Hi everybody, welcome back. We are going to be covering exponents and radicals today, giving it a pretty thorough treatment. So if you're in grade 10, this will be good because this is the first year this is covered in any great depth. Grade 11, it'll make a good review for working with radical terms, radical expressions, and solving radical equations. If you're in grade 12 and you are getting into logarithms, this is the precursor to logarithms, okay? So it's good for every high school grade. So let's get started. So first of all, let's talk about the exponent laws. So if we have x to the power of a times x to the power of b, that simplifies to x to the power of a plus b. Okay, so I'm going to do examples as I go on with numbers here. So 2 to the power of 2 times 2 to the power of 3 is equal to 2 to the power of 5. To prove it, 2 squared we know is 4, 2 cubed we know is 8, that gives us 32, and 2 to the 5 is 32, okay? X to the power of a divided by x to the power of b is x to the power of a minus b, okay? So if you have, let's say, 2 to the power of 6 divided by 2 to the power of 4. That's going to be 2 to the power of 2, which is 4. So 6 minus 4 is 2. Okay, so what we have here, 2 to the 6 is 64. Divided by 16 is 4. You can check that on your calculator if you don't believe me. Okay, then we have x to the a to the power of b. So when one exponent is being raised by another exponent, what we do is we multiply the exponents like so, okay? And an example of that, let's line these up. And an example of this one would be, let's say, 2 to the power of 3 squared, which is the same as 2 to the power of 6. 2 to the power of 6 is 64. Another way to look at it is 2 squared cubed. Because we can multiply numbers in any order, 2 times 3 is the same as 3 times 2. It doesn't matter where these numbers are. We're still going to get 2 to the 6. We're still going to get 64. So a way of looking at this one too is that it's 8. 2 to the power of 3. 2 cubed is 8. Squared is 64. And this one, 2 squared is 4, cubed is also 64, okay? So those are the main rules. There are a couple of others we can take note of. X to the power of 0 is equal to 1. So it doesn't matter what you're raising to the power of 0, it'll be equal to 1. So, for example, if you had something kind of ridiculous like this, 4, 5, 6, 7, 2, 9, 1, x to the power of 15, y to the power of 12, all to the power of 0, that's just equal to 1. It doesn't matter what it is. If it's to the power of 0, it will be equal to 1, okay? So that's the main rules for starting off. Now, let's look at a couple of examples. So let's say that we want to solve 2 squared to the power of 5. Well, we could go 4 to the power of 5. If we want this expressed as a power of 2, we would go 2 to the power of 10. Either way, we're going to get 1024, okay? Now, these numbers, it's good to have powers of 2 memorized up to a certain point because it's such a common base to use when you're learning to work with exponents and radicals. So it's not really that hard because you're either multiplying or dividing by 2, which in most cases is pretty easy. Okay, so I'm going to go up to 10 here just to show you that it's not hard to memorize. Hopefully that's still on the screen. 2 to the 1 is 2, of course, right? 2 squared is 4. Now we're just doubling these numbers as we go, right? It's not that hard to multiply by 2. if your second number that you're multiplying, so 6 is greater than 5, which means it's going to bump you above 10, then just multiply the 10 part by 2 and multiply the other part by 2. So if we multiply 16 by 2, here's the way we can do it. We can go with 10 times 2 plus 6 times 2, right? Using BEDMAS rules. That's going to give us 20 plus 12, which gives us that 32. Carrying on, 128, 256, 512, and 1024. Yeah, I've been doing this for a long time, so these numbers are second nature to me. But one way that I teach my students to try to remember them is most students can get up to here without too much difficulty. They don't have too much difficulty in remembering the powers up to this point. But beyond that, it gets a little trickier. So what I like to do, a little mnemonic that I like to use, is for 2 to the 5 fingers is 32, 32. Okay, so maybe that helps. Beyond that, you're just multiplying by 2. So maybe this is the one you memorize, and then you divide by 2 to get smaller powers of 2, or multiply by 2 to get larger powers of 2. This is another easy one to remember because 2 to the 10 is 1024. Okay, so sometimes it's a simple case of just finding a pattern, not a pattern so much here, but just something that'll twig, something that'll help you remember it. And for me, it's the fact that we have these two 10s, okay? Okay, now what about if we raise negative 3 to the power of 3? What's that going to be equal to? Well, what does this say? Okay, it says negative 3 times negative 3 times negative 3. That's what we're doing. Any negative base that is raised to an odd numbered exponent will be negative. These negatives will cancel out to give us 9, positive 9, and then when we multiply by that negative 3, we're going to get negative 27. So the negatives don't cancel each other out when the exponent is odd. Therefore, when the base is negative, your answer will be negative, your final answer, okay? Now that answer that we just got up here will be the same for this one. When the exponent is odd, it doesn't matter whether that negative is inside the brackets or not, you're going to get the same answer. It doesn't mean quite the same thing, but the result is the same. So this one, let's just put a 1 beside that. This one says negative 3 times negative 3 times negative 3. That will give us negative 27. What this one says, we'll put a 2 beside that one, says negative 1 times 3 times 3 times 3. Okay, they say different things, but the result is the same. Still negative 27. Now that doesn't hold true when the exponent is even. Okay, you get different answers then, so let's have a look. Okay, so how about this? Negative 2 to the power of 4. So we already know that 2 to the 4 is equal to 16. Because the exponent is even, we are going to end up with a positive answer, okay? And here's why. This is what we're doing. These negatives cancel out to give us 4, and so do these. And so, of course, 4 by 4 is 16, right? But now what if you had this? Now that is going to be negative 16, okay? And here's why. Because what you're doing is you're following those BEDMAS rules, right? BEDMAS says we have to do exponents before we do multiplication. So what exponent work do we have here? Well, we have 2 to the 4. It's the 2 that's being raised by the 4, not the negative. So in an expanded form, here's what this one looks like. Yeah? And this gives us negative 16, right? So be very, very careful with that. It's really important to take notice of those brackets, okay? Okay, now do you know about rational exponents? Do you know how they work? What is that telling me to do? When we have a fraction exponent, we have a little bit of more work to do, okay? So first of all, let's understand what's being asked of us here. Here is what this is written in radical form. Now, if you're not familiar with radicals, a radical is basically anything that has this square root sign wrapped around it, or cube root sign, or fourth root sign. Doesn't really matter what the index is. This is called the index. This thing there, that's called a radical, okay? Now, a number isn't necessarily an irrational number. That's a rational, irrational, and radical kind of mean the same thing, okay? This is actually not an irrational number. It's written in radical form, but it's not an irrational number. It's not a radical number because the answer is just 3. So what this is telling me to do is to take the square root of 9, okay? The bottom number is the root that we take, and the top number is what we raise the resulting root to. So let's look at a different example. Let's look at this one. Okay, what's that equal to? Well, what this is telling us to do is it's telling us to take the cube root of 27, so the number that's multiplied by itself 3 times to give us 27, which is 3, and then we square the result and we get 9. Now, how would we write this in radical form? Well, we would write it like this. We would put, so this number is the index, and the index goes in the notch, and the number that we're raising it to goes there, okay? So the way I like to think about it is the root that we take is on the bottom, okay? Roots like radicals, radishes, all come from the same root word. They're in the ground. Think of them as below, and that's why they're in the denominator. One teacher said, think of the denominator goes in the notch. Okay, it's silly, but it's a good way of remembering it. And the top number is the number that we raise it to. Okay, that's the number that is in the numerator position. That's the exponent. That's what we raise it to, like it's up on a shelf. Okay. Now, you could square 27 first and then take the cube root, but that would be hard because the number is huge. I don't even know what that is, okay? So why would you do that? No reason to. Take the root first, hold that number in your mind, and then square the result. All right, so what about this one? Well, can you take the 5th root of a negative? Yes, you can. You can take the odd root of a negative number, but you cannot take the even root of a negative number. Okay, we'll go into that more in a few minutes. The odd root of a negative will be negative. Okay, the odd root of a positive is obviously positive. Negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is negative 32. So the 5th root of negative 32 is negative 2. Then we raise that negative 2 to the power of 3, and we get negative 8. Okay? If we have this, what do we get? We get the same root to begin with, because the 5th root of negative 32 is negative 2. That's the same thing we were doing up here. But now we're taking that negative 2 resulting number and we're squaring it. We're raising it to an even number, which means it will be positive, for sure. Okay, it has to be. Because any negative times itself is, of course, positive, right? If we were to multiply by another negative, like we did here, because we multiplied negative 2 by itself 3 times, we end up with a negative result. Okay, so now let's look at a few different radical and exponent expressions and see what we do with them. So what we want to do with these 3 is we want to turn them into exponent form. If you haven't done this kind of thing before, you might be wondering how we go about doing it. Well, remember that if you don't see a number written in here, then there's an invisible 2 there. It means square root, okay? And then we have to decide, okay, what of this, what's under here? This is called the radicand, okay? The stuff that's under the square root sign or the cube root sign, whatever the case may be, it's called the radicand. And what we want to decide is, what is this radicand raised by? Well, the 3 is only being raised by 1. It's not being raised by that 5, only the x is. So this 3 has an invisible 1 exponent, and that means that it is to the exponent of 1 over 2. And then this x is being raised by the 5, which means it has an exponent of 5 over 2. Okay? Okay, to put this one into exponent form, we can start by doing this. So there's an invisible 2 here and an invisible 1 here. When you don't see numbers there, they are 2 and 1 respectively, okay? Now, this is perfectly good, but in a lot of these types of questions, what they're looking for is not something that's part of a fraction. So further simplified, it would look like this, okay? And we're going to go a little bit more into negative exponents in a couple of minutes here. But basically, when you have a base with any kind of an exponent, when you reciprocate the base, the exponent takes the opposite sign. Okay, and like I said, we'll talk more about that in a minute. Now here, we have the 2 is being raised by 1 over 3, because we've got an invisible 1 here, that's our numerator, and the index, which is this number here, meaning the cube root, is the denominator. The b is being raised by 3 over 3, but we wouldn't write that, would we? Because 3 over 3 is just equal to 1. So what we would write is the cube root of 2, that's what that means, and then we would just put the b beside it like that, okay? Now, negative exponents. We don't like negative exponents, okay, they're hard to work with. So whenever we get them, what we have to do is we have to get rid of them. 9 times out of 10, even more than that, you're going to be getting rid of that negative exponent to start the question. So for this one here, the base is 64, so if we flip the 64, take the reciprocal, we get 1 over 64. And the exponent is then positive, like that, okay? Now, you could write it like this, and I've gone over this in a previous video, but you probably wouldn't, okay? Because the 1 being raised by this 1 over 6, it could be being raised by anything, and it wouldn't change. So typically, we only write it on the number that it actually affects, okay? It doesn't affect the 1. I could raise the 1 to anything and still be 1. So then we just finish it off and we say, okay, like the 1, as I said, is just 1. And what is the 6th root of 64? It's 2. And be careful that you write 1 over 2 and not 2, because a lot of students make that mistake, okay? This one here, we have 2 numbers that we have to take the square root of, okay? So when you have a fraction and you have to take the square root or the cube root or whatever exponent treatment you have to do to it, just take each number by itself, okay? Then it becomes very easy. So the square root of 4 is 2, and the square root of 9 is 3, and you're done. Now this last one actually can't be done, okay? The square root of negative 9 is not a real number. In a way it does exist. It's a subject of higher math. The square root of a negative is called I, and it's used a lot in electronic engineering. We're not going to go into that in this video, but for your purposes, when you're being asked to take the even root of a negative number, you say it can't be done, okay? So you write that, can't be done, or not possible is another way of saying it, okay, not possible. So some people think it should be negative 3. You know, they say, what I ask them the square root of negative 9, they say negative 3, but it doesn't work. Because if you multiply, I know I'm running out of room here, you won't be able to see on the video anymore. If I multiply negative 3 by itself, because that's what square root means. It means find the number that multiplied by itself gives you that number. Well, I can't multiply any negative by itself and end up with a negative. I can't multiply any number by itself and end up with a negative. It's not possible. This is equal to positive 9, right? So this cannot be done, okay? All right, so how would you tackle this one? Basically what we want to do is we want to evaluate what we can and simplify what we can't, and also get rid of that negative exponent. So what I would do here, first of all, is I would flip the base. Now, this causes a lot of confusion. Because people think that as soon as I do this, so this is the base I'm flipping is this one here, this entire thing, okay? And that is the exponent that is raising this whole base. So when I flip this base, people think these exponents ought to change as well, but they don't, okay? Because I'm not flipping n as far as that 3 is concerned. So it's a little bit confusing at first, but eventually you start to catch on. It just takes practice like everything else. And now that I've flipped this base, this exponent that is -2 becomes +2. And now everything that's inside that brackets is going to get raised by that too. So n to the power of 3, remember when we raise one exponent by another exponent, we multiply those numbers. So that's n to the 6. On the bottom, you wouldn't write 2 squared. Okay, why not? Because you can do 2 squared. It's easy, it's 4, right? So you just write the 4. And then m squared to the power of 2 is 2, that 2 times 2. So it's going to be m to the power of 4. Okay, we're not adding those 2's, we're multiplying them. So eventually you're going to come up with preferences on how you tackle some of these more complex ones. This one, it looks really nasty, but it's actually not as bad as it looks. So the first thing that I want to do here is I want to simplify what's inside the brackets and ignore that entirely. And that brings up a very important concept here with negative exponents when you're dividing them. Okay, let's start by looking at something else for a minute here. So what's that equal to? Well, you know that when we divide bases, we subtract exponents, right? You know that what we have here is that. So if you cancel the things that can cancel, what you're left with is x squared. Now notice that that's just 5 minus 3. There's your 2. Okay, so it's very, very simple process. You just subtract. But what if you have this? So when I ask my students what this results in, a lot of times they tell me it's this, which is not wrong. That's correct. Which then translates into this, because remember when we have a negative exponent, we like to get rid of it by flipping the base, taking the reciprocal of the base, which is x, and then we end up with 1 over x, and then the 2, the -2 here becomes a +2. Okay, that's the rule. Well, what you can actually do is you don't have to go through this middle step. You can just say, well, okay, you know what? The larger of the 2 exponents on this x is on the bottom. So that's where my x will land. And then you subtract from the bottom up. That's it. That's all you have to do. It's the same process that we did a second ago when we had the 5 on the top and the 3 on the bottom. We're still just canceling out those common x's. Where this gets a little bit more dicey is when you have negative exponents. So let's say I have this. What this requires is just a little bit more care and thought, okay? So the first thing that I like to do here is I like to draw a new fraction line. If everything ends up in the numerator, you can always erase it, because you should always be working in pencil in math, okay? So first of all, I look at the x's and I say, where is the larger exponent on x? Well, it's in the denominator, isn't it? Because -1 is a larger number than -3. So I'm going to put my x there. Now, what is the exponent? Well, what we're doing is we're going -1 minus -3. Okay, it's not -4. Okay, that would be -1 minus 3. So you have to really watch your number line work here. -1 minus -3. Here's what we're doing. -1 minus -3, which is -1 plus 3, which is 2. So that's what that exponent is. A lot of mistakes are made here, okay? And it's because subtracting negative numbers is difficult and it's easy to get lost. So all you have to do is you have to at least think this, even if you don't say it, okay? -1 minus -3 is -1 plus 3, because these two negatives are getting multiplied to make that plus. If you do this method, you will never end up with a negative exponent over here. It'll never happen, ever, okay? Because you're always starting from the larger number and then you're adding. You're adding a number, and you're always going to end up in positive territory that way. So for this one, the larger number of these two exponents is on the top, so that's where my y is going to go. Now what's -2 minus -4? Again, you have to at least think this even if you don't write it out. That's -2 plus 4, which is 4 minus 2, which is 2. Okay, so that's the exponent that y is going to get. And then the z, the higher exponent is on the top as well. So let's put the z there, and then let's think about what the exponent is. So we have 4 minus -3. So whether you're working from the top down or from the bottom up, you're always subtracting, okay? 4 minus -3 is 4 plus 3, which is 7. And that's the exponent that z gets. Some people really dislike negative exponents, and they deal with them this way. So here's what you could do. You could say, okay, I'm going to move all my negative exponents into the other position so that they're positive, which would put this x to the top and this x to the bottom with a 3. It would move both of those y's. We'd have that, and we'd have that. And it would not move this z to the 4 because that 4 is positive, and this one would move to the top. Now, you're still dealing with negatives in a way, because if you go 1 minus 3, you're going to get -2 right on top. So here, it's best still to work from the bottom up, because that's where that larger exponent is on x. So you put the x there, you go 3, that 3 minus 1 gives you 2. Here, 4 minus 2 gives you 2, right? And here, we're not dividing these bases, now are we? We're multiplying them, so then we're adding those exponents, which gives us that 7. And notice I have the same answer, right? So this is an okay method. This one here that I did here, moving things around, it's an extra step. It's one you don't really need to take. But what I kind of don't like about this method is if there was a 2 here, I guarantee you that 2 would get moved. Because people would think it's locked onto that x. It wouldn't be, okay? And that's why this method is not really the best. I think this is the best method, okay? And then doing this stuff either in your head, saying those words to yourself in your head, or writing out the math, scribble it off to the side in your margin, okay? Okay, so now that we've covered that, let's go back to this question. So what I'm going to do is I'm going to simplify everything in here first, and I'm going to leave that -2 on the outside for now. So if I do this, 4 over 8 is 1 over 2. I'm not going to put the 1 down unless nothing else ends up in the numerator, and then I need to put a 1 there in order to hold it. The larger exponent on my x, it's on the bottom, so that's where my x is going to go. And then I'm going to do what I said you should do, which is 2 minus, so 2 minus -3 is 2 plus 3, which is 5. So that's the exponent on my x. And then the larger exponent on my y is on top. So I put the y there, and be careful that you don't go 4 minus 2 and put a 2. It's not 4 minus 2, it's 4 minus, because when we divide bases, we subtract exponents. So it's 4 minus -2, which is this, which is 4 plus 2, which gives us 6. So then you put the 6 up there, okay? Now that is still all to the power of -2, because I haven't flipped anything yet. This is an equivalent expression to what I have here. Exactly the same, okay? Now what I'll do is I'll flip this base. So the denominator becomes the numerator becomes the denominator, and now I have a positive exponent too. And now I can apply that 2 exponent to everything that's inside the brackets. So 2 squared is 4, x to the 5 squared is x to the power of 10, and y to the 6 squared is y to the power of 12. Okay, and now that one's done. Okay, this one looks a little scary, doesn't it? Okay, what do we do with this? First of all, it might help to rewrite it slightly so that we're clearer about what we're flipping if we decide to flip this entire base first in order to make this positive. There are lots of ways to deal with these questions. It comes down to preference, okay? And what I'd like to do here, I think, is I'd like to rewrite it like this. Now it's kind of a shame that the only thing not being raised by that -4 is the 3 over 2. Because if this was being raised by a negative inside the brackets, then I would apply that -4 to everything that's in here right now, and it would create positive exponents across the board, and I wouldn't have any more trouble with it. Unfortunately, that won't be the best method to use here. So I think what I'd like to do is get rid of this -4 first rather than applying it first. So I'm going to flip the base, which is going to give me 2 over 3m to the -2 n to the -3 all to the power of +4. Now again, it's a little awkward here because it would have been nice if I had multiplied the -4 times the -2 and the -3 there. I would have eliminated those negative exponents entirely. But then I would have had to do the same to the 3 and the 2, and now the 3 and the 2 would both be to the power of -4, and that's awkward. So I think this is the better approach for this particular question. Now I'm going to apply that exponent 4 to everything that's inside the brackets. So 2 to the 4, remember it's not 8. So what we're saying is this 2 has to get multiplied by itself 4 times. I had listed the powers of 2 earlier. 2 to the 4 is 16. And 3 to the 4, okay, it's not 12. Be careful. It's not 3 times 4, it's 3 times 3 times 3 times 3. 3 times itself 4 times. So here's a way that you can think of 3 to the power 4. You can think of it as 3 squared squared. Same thing, because 2 times 2 is 4. Now 3 squared is 9. And 9 squared, pretty much everybody knows this one, is 81, okay? So that's how you can deconstruct a higher power so that you can solve it more easily in your head. Okay, so we got an 81 there, and then the m to the -2 and the n to the -3 have to be raised to that 4 as well. So we're going to get m to the -8 and n to the -12. Now all we do with those, we'll come over here to finish this, is we're just going to pop them into the numerator. Okay, we're reciprocating these bases, and we're going to end up with positive exponents as a result. Okay, so here's what we kind of have. We have 16 over 81 times 1 over m to the -8 and n to the -12. And then these just got moved into the numerator and multiplied by the 16. It's just a different way of writing it, okay? So this is what this is, and then those two just got moved to the top to give our positive exponents, and then we just snuck it all back together again. Okay, but that intermediate step, you absolutely do not have to write it, okay? Okay, so in the current grade 10 math textbook being used in Alberta, this is one of the harder questions in the book for exponents, and I wanted to go over it with you. What makes it hard is that we have to do all this exponent work. This exponent has to be applied to this, and that exponent has to be applied to that before we can do any division at all, okay? Because remember, BEDMAS rules say that exponents have to be done before division. So it's awkward because this is a negative exponent. So here's one way you can deal with this one. You could write 2 to the negative 2 and then apply that negative 2 to each of these exponents for the numerator. That would be one way to start it. Here's another way though. You could take that entire, this whole thing here, and move it into the denominator. So then you would have 2a to the negative 4, b to the 4, c to the negative 3 to the power of 2. And that's just on 1. And then that's times this stuff, which is also on 1. Okay, I think this is the best way to deal with this question. So now what we'll do is we will apply these exponents, this exponent to what's in here, and this exponent to what's in here, and then we'll bring the two fractions together. So we have 1 over 2 squared is 4, a to the negative 4 squared is a to the negative 8, and I'll just write out what these are. Four squared is 16, a to the 4, b squared, c to the negative 8. And now what we're doing is we're just bringing these two together. So all right, so now our final answer, nothing is in the numerator. I don't think anything ends up in the numerator. 4 times 16 is 64. A to the negative 8 times a to the 4. So we're multiplying these bases, so we add the exponents. Negative 8 plus 4, oh, we do end up with something in the numerator, because what we end up with here is negative 4. That's the power on that a, okay? B to the 8 times b to the 2 is b to the 8 plus 2, because we add the exponents when we multiply the bases, so we end up with b to the power of 10. And then negative 6 plus negative 8 is negative 14. So we get c to the negative 14. I'll just put a 1 there to hold that for now, okay? Now that's not wrong, but it's not finished because we want positive exponents. So what we're going to do is we're going to move the a and the c into the numerator. So we have a to the 4, c to the 14 over 64, b to the power of 10. And that one's done. Okay, so that's it for this video. Please give me a thumbs up if you liked it. Please share widely, and we'll see you next time. Thanks a lot.